So I'm currently working at Goldman Sachs. I've been in New York for about a year and a half. This is actually my first stint in finance, so it's been fascinating for me to learn about the world of banking, the world of trading, the world of asset management, and also the world of actually consumer banking, because Goldman Sachs is now a leading deposit taker and a leading lender to consumers. And that was actually part of the reason that I chose to join Goldman Sachs, because that's a consumer business, so that's related to what I was doing at Amazon. Let me start with a little bit of a history lesson. So as you heard in the introduction, I'm really an academic. I was a professor for a long time at the University of California in San Diego. I've been a visiting professor here in Boston a couple times. We heard at the beginning this morning about how there was an AI winter in the 1990s, and I lived through that. Fortunately, I had a university position, and so I wasn't in danger of losing my job. But certainly there was a lack of interest in artificial intelligence at that time. In fact, I remember going and talking to the dean of my college at my university and telling him that I was working in artificial intelligence, and he frowned. He didn't think that artificial intelligence was something appropriate for someone in a computer science department to be working on. He's retired. Yeah. So just a little bit of the history of artificial intelligence. I like this picture a lot, partly because it shows one of my own advisors, John McCarthy, who was one of the founders of artificial intelligence. But I like it even more because it's so obviously staged. And the tropes that are in this picture were what people were thinking of in the 1960s about artificial intelligence. I think this picture is from 1967. And then really people are thinking the same things nowadays in 2019. So people are in awe of big data and big compute. Well, this is the big compute of 1967. And then there are certain applications which seem to stick in the public perception as being quintessential examples of intelligence, and game playing, and in particular playing chess. Well, it's actually more than 20 years since computers have been better than the human world champion at playing chess. And we still don't have general artificial intelligence. So in fact, playing games, whether it's chess or whether it's games that computers have become champions at more recently, is not a very good indicator of the state of artificial intelligence. And an algorithm, a piece of software that's good at playing a game, is not an algorithm that has general intelligence. In my own work and thinking about applications, what I find it always very useful to think about is decisions versus predictions. So machine learning, at its essence, is about using data to come up with models, and then those models can make predictions. But whether it's Amazon or whether it's Goldman Sachs, what we really need is better decisions. So let's say we have a credit card transaction, and we can predict that there's a certain probability this transaction is fraudulent. Well, the prediction is good to have, but what we really need from a business point of view is a decision. Do we approve the transaction or do we reject the transaction? And then decisions have consequences, and decisions have costs. There's a cost for being wrong. If you reject a legitimate transaction, then you've annoyed the customer, and there's a significant business cost to that. So decisions are always where I start when I'm thinking about a business application. The other starting point is automation versus reporting. People often use the phrase data science is very popular. I prefer the phrase machine learning, partly because that connects it back to what's the underlying technology and what are the real advances, because people were doing data science 100 years ago, and partly because machine learning tends to put the focus on autonomous systems that are making decisions continuously in real time, and that's where the business value tends to come. If we're only generating reports, and then that's a nice to have, but quickly it becomes information overload, and quickly you start asking, well, where's the real day-to-day continuous business value? The example from Amazon is, we can generate a report about which customers are more likely to buy shoes, but so what? What we really need is real-time recommendations of shoes to customers who are likely to buy shoes if we show them the recommendation. And then actually we can get a little bit more sophisticated. really we want to recommend shoes to customers who are likely to buy shoes if we show them the recommendation, and then less likely if we don't. Because if the customer is going to buy shoes anyhow, then why should we use the real estate to recommend shoes? Maybe we should use the space on the screen to recommend something else where we can actually influence the customer. All right. So why is the world so excited about artificial intelligence nowadays? As I said, I've lived through the AI winter. Well, I think there's a very simple answer, and it's a two-word phrase: deep learning. And if you have some familiarity with the history of science, you know that this concept of normal science and then paradigm shifts, scientific revolutions, coming from Thomas Kuhn. Well, deep learning is maybe a medium-sized scientific revolution. It's definitely enabled a new wave of normal science in machine learning and artificial intelligence research. And where has deep learning particularly enabled progress? In computer vision and in natural language and in the combination of computer vision and natural language. And I think it's the combination of computer vision and natural language that really gets people excited, because this really seems like a step towards a human type of intelligence, even if it's not a human level of intelligence. And then why are people in business excited? Because deep learning does yield higher accuracy in many applications, including forecasting, which we heard about earlier this morning. So on the left here, I have an example of what we can do using deep learning that we couldn't do with any previous methods. So here's a photograph. It's a bicycle, and on the carrier there's a box of donuts. And then we have a question: how many leftover donuts is the red bicycle holding? And this is a training example for the deep learning system. So the ground truth answer is provided, and here the ground truth answer is 3. And if you provide enough training examples of image, question, answer to the deep learning system, then the system can, once it's been trained, it can actually provide the answer to new questions about new images. So certainly this is a very exciting capability which we can achieve with deep learning, and there's no other technology that lets us come anywhere close to this capability. So what is deep learning? It's the current generation of neural networks. Neural networks were actually invented in the 1950s. It's the same decade at which the field of artificial intelligence really began. They are inspired loosely by neuroscience, but one of the challenges of research in artificial intelligence for the past 60 years, and it's a continuing challenge, is what can we learn from biology that is useful for engineering versus what do we have to invent from scratch in engineering that isn't similar to human or animal biology. It's rather analogous to the challenge in aviation. So birds and airplanes are subject to the same laws of physics, but airplanes don't operate on the same principles as birds. And artificial intelligence doesn't operate on the same principles as neuroscience. So there were great research advances in the 1980s in neural networks, sort of mini Kuhnian revolution. And then there was a generation of applications that were enabled in the 1990s. And then there was really some stagnation in the research on neural networks. And then there was a new wave of progress in the 2010s, in the early 2010s. And something I think people don't appreciate is that artificial intelligence does exist in successful applications ever since at least the early 1990s. And it was actually one of my colleagues at the University of California, San Diego, who founded, as far as I know, the first company ever to have $1 billion IPO in artificial intelligence. And that company is called HNC, Heck-Nielsen Computing. And what they developed was a neural network technology for real-time scoring of credit card transactions. So ever since the early 1990s, if you swipe your credit card and that transaction is approved or rejected, for most credit card transactions in most of the world now, there's a neural network behind the scenes that is evaluating the probability that the transaction is fraudulent, and then there's decision-making logic on top of those predictions. The other big financial application of neural networks ever since the 1990s is automatic reading of handwritten checks, which is also done using neural networks. Well, nowadays, in the late 2010s, current deep learning exploits modern computational power. So it really is the case that we have orders of magnitude more compute power than even 10 years ago. And we also have massive data. And I have a little bit of a contrarian point of view on data. The saying that I like is that data is a cost, not a benefit, because it's very costly to collect data. It's interestingly, it's costly to collect data in terms of direct cost, but it's also costly in terms of risk, because as we heard in Alex's talk, if you have data, you always are at risk of that data being revealed to people that you don't want it to be revealed to, and then that can be a great cost. So actually at Amazon, we're actually careful not to collect data that we don't need. And we don't want to store data that we're not using, and that it would be a risk if we lost control of that data. But we do have massive data, and traditional statistical methods are really too simple for massive data. They were designed for much smaller data sets, and neural networks are a very important category of method that can actually take advantage of massive data sets and can take advantage of data of new types, like text, image, video. So it's just an illustration of a neural network on the right here. We at Amazon, we used deep learning for forecasting. So again, artificial intelligence has been around for a long time. Technology companies like Amazon have been around for a long time. I think Amazon is 27 years old at this point. And Amazon has been doing demand forecasting for the tens of millions of products that it sells for the whole history of the company. And so we were using traditional statistical methods, ARIMA methods, and then handcrafted variations on top of those. But we saw the opportunity to use deep learning for forecasting, and in particular, we saw the opportunity to use product descriptions, which are essentially text, as input to increase the accuracy of the forecasts. And the really difficult forecasting problem that Amazon has is cold start forecasting. So every day there are thousands of new products that come into inventory. And we need to forecast how many of those that we're going to sell, even though we don't have a history of how many we've sold because they're new products. But for every new product, we have a description. So for example, if something is a bikini, we have the keyword bikini. And we know the seasonal pattern of sales for bikinis in general. So using the seasonal pattern of sales for other bikinis and the fact that this product is a bikini, that we have the keyword, then we can combine the time series and the product descriptions into forecasts for brand new products. And so the figure on the bottom here is just a sketch of the architecture of the neural network that we, one of the neural networks that we're using for forecasting. Of course, there's continuous refinement. And then in the top left is an illustration of what the method's capable of. So essentially, the black curve is the actual demand for a product. The blue curve is the forecast demand for the product. The shaded blue region is the 90% confidence interval for demand, because it turns out it's not very useful to predict a single number for the demand for a certain product. What we really need is to predict a confidence interval. And then there are 4 different sample products. You can see the great complexity and variation in the demand curves for products. And what we really want is for the true demand, the black curve, to be within the blue shaded region. And that's the case for these examples. It's the case for most products, fortunately. And of these 4 sample products, the bottom left one shows what we can do with cold start forecasting. So here's a product which only came into inventory in the middle of 2016. That's why the demand for it is a flat line before the middle of 2016. And then with just a tiny bit of data up to the vertical blue line, that data along with the product description is enough to give a very reasonable forecast for the demand of that product. So definitely, deep learning is the state of the art for forecasting, especially if you have side information that you want to bring to bear. And I think in practice, you always have side information. All right, so what can deep learning not do? So I have an academic background. I never like to oversell things. I always like to understand things. What's the foundation? What are the fundamental challenges, opportunities? And I would say that what we don't have in current artificial intelligence methods is what I would call deep understanding. And also, if you're an academic, you don't want to throw buzzwords around. You actually want to have precise definitions for any words that you use. So what's a precise definition for the word understanding? So I want an operational definition, and I'd say understanding is the ability to answer questions. If a student understands something, then you can ask them questions and they give you good answers. And if a student has better understanding, then they can answer more questions and they can answer more different types of questions. So I'd say that's what understanding is. Then shallow understanding is the ability to answer a limited range of questions where the questions are similar to each other. So think of an AI system that can play chess. It can answer the question, which piece should I move to which square given a board configuration? And really that's the only type of question that it can answer. And it can answer that question very well, but it can't answer any question. It can't even answer the question, what is the name of the game that you are playing? It doesn't have any natural language input. The deep understanding is understanding that operates at multiple layers. It's understanding that can bring in outside knowledge, and it's understanding that can involve the context of the question that is being asked. And I think it's really interesting if you go back and look, how have humans been thinking about the nature of intelligence for thousands of years? Well, the etymology of the word intelligence actually comes from the Latin intelligere, and the root meaning of that is to choose between, to select between. So I really think the ability to choose between different answers to questions is the essence of intelligence. So I used a story about this example. So the first time I gave a presentation with this as an example, it was actually for the Amazon board of directors, because Jeff Bezos is very knowledgeable about machine learning. Machine learning is of ever-increasing importance for Amazon, and so he thought that the directors of the Amazon company should know more about machine learning. And so I was giving this presentation explaining what deep learning can do, and then Jeff actually put his hand up, and he said, hey, why do you say the answer is 3? The answer is 3.5. And in fact, if you look at this picture, there's 3 donuts in the top left of the box, but then there's what looks like fragments of a half-eaten donut in the bottom right of the box. So 3.5 is a correct answer to the question. Well, now let's think, so if there's 2 different answers to this question, is there a third answer? Well, I think yes. The third answer might be 3 and 2 fragments, because we can't actually see a half donut. We can only see the 2 ends of a half donut. So literally what's visible is just 2 fragments. So we have all these different questions, and we have, all these different answers to the same question, and the different answers are valid depending on the purpose of the question. So again, it's not really about making a prediction, or it's about what do you want to do with that prediction. So if you want to know how many people can you feed using the remaining donuts, the answer is probably 3, because nobody wants to eat somebody else's half-eaten donut. That's an example of bringing in knowledge about social conventions among humans to answer a question that at first sight is just a question about what's in a picture. And then, why can we say there's a half donut? Well, we understand about gravity. If there were really 2 little pieces of donut, they wouldn't stay suspended in air. They would fall down and we wouldn't see them. So a deep understanding this is an example of deep understanding where the same question can have multiple answers, and then the different answers have different explanations, and they involve background knowledge. Right. So what are the consequences of shallow understanding? Most applications remain brittle. And brittle is actually a technical word in artificial intelligence, which people have been using certainly for many decades to describe the phenomenon that you can build an AI application which is successful in a very narrow domain, but then when you change the domain a little bit, the application will fail, and it won't even know that it's failing. It won't be able to tell you that it's failing. And we've seen, we've seen many examples of this recently in face recognition. Maybe you change the lighting and the face recognition stops working. Street sign recognition, you can make adversarial examples. You change a few pixels in the image and the recognition of the street sign fails completely. And question answering. So here's an example from Alexa. So, voice assistant. So you can ask it, Alexa, how high is Mount Everest? And then you get a good answer, a whole sentence, 29,029 feet. And then, if you have a follow-up question, Alexa, where is it located? Well, I've been tracking Alexa and trying this question on Alexa for many years. Alexa is 5 years old at this point. And as of a few months ago, the answer that I would get was, the address is 318 3rd Avenue. So it turns out there's a restaurant that has the word Mount Everest in its name, which is located at 318 3rd Avenue. Now, what linguists call this anaphora. So the word it in the follow-up question, it's very easy for a human to understand that it refers to Mount Everest and it refers to Mount Everest, the mountain. It doesn't refer to Mount Everest, the restaurant. Interestingly, I just tried this question again yesterday evening, and Alexa gets this right now. So there is progress, but it's public information that the number of people working on Alexa at Amazon is over 10,000. And actually in the previous talk, we heard about how Uber has this system which will take in a question and then understand the intent of the question and then suggest recommended answers. Well, Alexa and all other voice assistants actually work in roughly the same way. The sentence comes in from the human, and then it's classified according to the intent. And then once you find out what the intent, you fill in the slots which specify exactly what the question is. So how high is Mount Everest? One slot to fill in is the word high, so we're asking about height. Another slot to fill in is Mount Everest, so we're asking about this mountain and not that mountain. And every different intent essentially corresponds to a different team of engineers and scientists who are programming in the response to that type of intent. And I guess the 10,000 people sometime in the last few months, they got around to programming in how to answer this particular type of follow-up question. But what is it that you're very resource intensive in human intelligence to have the appearance of artificial intelligence. And something which is closely related, AI systems need excessive quantities of training examples compared to a human. So here we are in Boston. There's a local adverb, wicked. It's wicked cold outside. And I think probably most of you know what the word wicked means, but even if you didn't, you come to Boston, you hear people say this probably 1 or 2 times, and you'll already have figured out, and probably unconsciously, what do they mean when they say wicked, and then you'll be able to use it when you're talking yourself. So you can learn the meaning, a new meaning for this word with just 1 or 2 examples. Well, AI systems need far more examples. If a human is learning to drive, maybe you're in a Western country, you're a child, you're being driven around by your parents for 1,000 or 2,000 hours, while you're a child. So you learn by observation how to drive unconsciously, and then you take 10 or 20 hours of driver ed, and then you know how to drive. And you may not be a great driver, but that's probably actually more because you're a young person who takes risks than because you actually don't know how to drive. Whereas all the companies that are developing self-driving automobiles, they are using literally millions of hours of training data. So literally 1,000 times or more the amount of training data that a human would need to learn to perform the same task. So if I don't want to be really a downer on artificial intelligence applications, so let me give you an example of something that I think is really wonderfully well-targeted, designed application. And this is actually a company, full disclosure, that Goldman Sachs is an investor in, but I came across this example before we invested in this company. So there's a big problem in the United States. Healthcare is very expensive. There's a shortage of primary care physicians, nurse practitioners, and the productivity is pretty low. The average primary care visit takes 25 minutes. So a physician can only see, 16 patients per day or something. Well, this company has reduced primary care visits from 25 minutes to 9 minutes, and while keeping the patient satisfaction scores up, and while keeping the provider satisfaction scores up. The way they do it is with an app, and the patient describes his or her symptoms in free text, and then the app uses machine learning to select follow-up questions. So again, this is pretty similar to the Uber application that we just heard about. And then the patient provides answers to the follow-up questions, and then the questions and answers are all given to the physician. And the physician can read these very quickly, and in the worst case, the software chose the wrong follow-up questions, and the patient hasn't provided the useful information. So then the physician can ask questions using his or her deep understanding. But in the common case, the app has asked the right questions, and the physician has now essentially done the first half of the primary care visit in 1 minute rather than in 15 minutes. Then the physician is still making all the decisions, the medicine, the advice, the referrals. So this is a human-machine partnership where the machine is providing the automation and the shallow understanding, and the human is providing the deep understanding. And this company has picked a great application. They've picked a great way to attack the application, and so they're really being very successful. And they couldn't do this without artificial intelligence. So I think I just have a couple minutes to talk about machine learning specifically in finance. One of the interesting things about working at a place like Goldman Sachs is Goldman Sachs has employed thousands of people with PhDs for many decades, and these people are all very quantitative. So there's a complete continuity between their skill set and the skill set that is involved in machine learning, artificial intelligence. So what is the difference between machine learning and other quantitative scientific methods? I think the fundamental difference is that most of the methods that have been traditionally used in finance are deductive. Essentially, you start with some axioms, like some principles for how prices follow a random walk, and then you deduce some consequences. And economists have won Nobel Prizes for deducing consequences in finance from axioms about how prices move. Machine learning is useful for tasks where there just isn't much opportunity for deduction, for tasks where there's intrinsically an empirical component and there isn't a single theoretically correct answer. So as an example of that, estimating a market price for a real estate asset. So Goldman Sachs, other financial firms invest in real estate, and you need to know what's a fair price for a real estate asset. Well, there's no theory that tells you the fair price. It's all based about comps, and then maybe it's based also on what you can predict about the future, like what are the patterns of, what are the changes in popularity, changes in movement. We heard about some of that in Alex's talk. So it's totally empirical how different locations, roads, lot sizes, room types, style influence the prices of a house. And the transaction price for a house is going to have a probability distribution, and it's not a standard distribution. It's not a Gaussian. It's not a binomial. It's just got a strange shape. It's empirical. And then we have new types of data that we can use as input. Maybe there's there's local news which affects the value of a real estate asset. We can use photographs to tell us, is this asset in good condition or in bad condition? And actually this, I can't tell you the exact problem that my team is working on, but we're having a lot of success, using machine learning, using deep learning for estimating market prices for very illiquid assets like real estate assets. And even real estate assets, very relevant to Goldman Sachs. One of the things that Goldman Sachs does is, well, opportunistic, maybe that's a bad word, just investment in real estate, and you want to be able to efficiently screen the real estate investment opportunities, and so you want to have machine learning methods that can provide a baseline estimate of value. What have I learned about actually driving successful projects that use machine learning? Well, one thing actually that I've learned is essentially you want to start with a big opportunity. I think you heard, my team at Amazon, we did have a couple big wins. Our biggest win was several $1 billion in revenue, which translates to maybe $100 million in profit, because the retail business is actually a relatively low-margin business. And how do we get a win of several $1 billion in revenue? We improve a business that already has several tens of billions of dollars of revenue. So there's no secret there. You got to start with something big, and then if you can improve it, you get a big improvement. And how do you improve something? So what I've learned is that you really need a product manager. And if it's a small project, maybe you don't have somebody who's designated as a product manager, you just need somebody who acts as a product manager. So when I interview candidates for my team, I'm always trying to figure out, is this somebody who can be their own product manager? And what does a product manager do? The way I put it is that a product manager is the voice of the user when talking to the developers, and a product manager is the voice of the developer when talking to the users. So you need to be realistic when you're talking to users or customers, and you need to be imaginative also. Here's this technology, we could do something cool with it, would that be useful to you? So that's the voice of the developer talking to the customer. But then the developers should always be thinking, what we're building, is it useful to the user, is it useful to the customer? So that's being the voice of the user when talking to the developer. And so some of the things a product manager does, quantify the size of the business opportunity. I just talked about that. For machine learning applications especially, figure out exactly what metrics should be maximized. Just as an example of that, so something my team worked on at Amazon was video recommendations. So product recommendations are a pretty mature field at Amazon, but video recommendations are more open-ended. So we worked on that. And so what are we trying to optimize when you do video recommendations? And a naive idea is, okay, we want to maximize the number of minutes that people watch movies and TV shows. But actually, that's really not a good objective, because if you have somebody who's already watching 200 minutes a day, then it's probably not beneficial to anyone to drive them from 200 minutes a day to 300 minutes per day. But what we really want is we want our customers who are not watching videos to start watching videos. And so we actually spent a long time going back and forth trying to figure out, well, what is the metric that comes closest to capturing what our real long-term business objective is? And we ended up on something like number of weekly active users. So if somebody is watching video at least once a week, they're a good customer. And if they're not watching video at least once a week, then they're a less good customer. So number of weekly active users is much closer to the metric that we want to maximize than number of minutes watched. But the difficulty then is that weekly active users, that's much more lumpy than number of minutes. So I could go into all those challenges. But a product manager needs to take the lead in figuring out what are you actually trying to achieve. Much better to have an approximate solution to the right problem than an exact solution to the wrong problem. And I don't have time to go through all of these. Guardrails and monitoring are very important, as we've heard before. Understanding the true business process. we're a bank at Goldman Sachs, so we're very interested in minimizing losses on loans. And people talk about what's the probability of default, what's the probability that the borrower will stop paying, and then what's the loss given default. If they stop paying, how much can we recover from collateral, for example? Well, and we have a lot of data about defaults, and we have data about recoveries. But it turns out what is much harder to get data about is these things that are called loan restructurings. And loan restructurings are when a loan is heading towards a default, and everybody knows it's heading towards a default, and so we renegotiate the loan, and it doesn't get categorized as a default. This is what's been happening just this week with WeWork. They've been renegotiating everything. I picked this as totally public information from the New York Times from 1990, new terms for Trump from big bank lenders. So, when Trump was a real estate developer, he was getting big loans from banks, and not all of those loans were really heading towards being repaid. So what happened, the loans were renegotiated. They were restructured. And those were real economic losses for the lenders. The lenders would never have made the loans if they had known that the loans were going to be restructured. But are those restructurings recorded as actual defaults? Are they data for probability of default? Are they data for loss given default? No, they aren't. And so this is also an example of where if you're not careful, data is a cost, not a benefit. Because if you're just using the data that you have, and you're modeling the data you have, and you're not taking into account this broader context of data that you don't have, then you're going to go in the wrong direction. Risks for a machine learning application, I could go on with a very long list of risks. The one that I want to focus on, just the last one here. The machine learning method is held to a higher standard than humans, or to a higher standard than the current business process. This is a real risk. And I like this picture as an illustration of it. So here is a neural network that detects drugs. And based on the output of this neural network, people get detained and questioned. And this is a drug-sniffing dog. And is it explainable what this neural network is doing? No. Is there any transparency into what data was used to train this neural network? No. But this is a natural intelligence method that is in use currently. If anybody wanted to use an artificial intelligence method to replace or augment these drug-sniffing dogs, I'm pretty sure that the artificial intelligence method would be held to a much higher standard than the current natural intelligence method.